These vintage transistors represent the absolute hardware baseline of how a computer operates. A computer has no brain. Its function relies entirely on physical components, either blocking an electrical current or letting it pass through. We see another physical state inside this open hard drive. Instead of electricity, the system relies on magnetic polarity. Tiny regions on that metal platter physically align to point either north or south. Computer engineers map those raw physical states, electricity on or off, magnetism north or south, directly into mathematics, assigning them the digits 1 and 0. This visualization shows how ones and zeros turn into numbers. In the binary sequence 1001, each position is a power of 2. Working right to left, we have 1 1, 0 2s, 0 4s, and 1 8. Summing those gives us the decimal 9. While binary math is the foundation of computing, it reaches its limit the moment we try to represent the complexity of the real world. Early digital color was restricted by this hardware. Engineers allocated just one on-off bit for each primary, red, green, and blue light. This 3-bit limit created exactly 8 colors, visible where the circles overlap into cyan, magenta, yellow, and white. Text representation faced a similar wall. The original ASCII standard, designed to translate bits into characters, relied on a strict 7-bit system. This 7-bit restriction resulted in only 128 available slots. That barely covered the English alphabet, basic numbers, and simple punctuation marks. Human reality consists of millions of colors and thousands of languages. Moving past these 8-color and 128-character limits required a massive engineering upgrade in scale. To expand the palette, engineers increased the memory space for each color. Red, green, and blue were moved from a single bit to a full 8-bit byte each. Giving each color 256 states changed the math. Multiply 256 by 256 by 256, and you get over 16.7 million total colors, enough to cover the entire range of human vision. This created a new problem: data readability. A human developer cannot accurately read or write 24 individual ones and zeros just to identify a single shade of green. Hexadecimal abstraction solved this by mapping every 4 binary bits to a single character, ranging from 0 to F. The contrast between these two rows shows the efficiency. A long, unreadable 24-bit binary string collapses into a neat 6-character hexadecimal code, like BC002D. The computer still processes the raw ones and zeros. Hexadecimal exists purely as a bridge to help humans manage massive data scale without getting lost in the binary sequence. Global text encoding followed a similar path. As computing expanded, developers tried to patch ASCII with regional ISO codes for different European languages. These regional patches were incompatible. Opening a document with the wrong encoding turned specific letters into entirely incorrect random characters. This led to the creation of Unicode, a standardized system that assigns a unique, permanent mathematical code point to every character in human history. Unicode accommodates the Latin alphabet, thousands of Chinese Hanzi characters, and modern emojis within a single system. This bar chart shows how we save that data efficiently. While UTF-32 wastes space by assigning 4 bytes to every character, UTF-8 dynamically scales. It uses 1 byte for a basic letter and expands to 4 bytes only for complex emojis. Unicode and UTF-8 allowed computers to encode the entire spectrum of human expression without wasting digital real estate. We can now encode millions of colors and characters, but a single text file containing all that data is impossible to search quickly. A cafe owner's paper notebook works for tracking 10 drinks, but the system fails when trying to analyze 10,000 orders to find the most popular item. The database is the ultimate organizational solution, a digital structure designed specifically for instant searching and sorting at scale. We see that organization in these structural labels. Columns dictate the type of information, like price, while rows hold the complete record. Using SQL, we ask the computer questions. It isolates the price column and retrieves the cheapest drink instantly without reading every row. SQL serves as the final translation layer, turning human questions into machine-speed retrievals. From the magnetism on a hard disk platter to the rows of a database, These layers transform raw electricity into structured logic. The modern digital world functions because we found a way to engineer scale into every individual electron.